So yeah, welcome, Sergey. It's a pleasure to have you here. As Sergey is going to talk about generalization and data-driven control. I was really surprised by the bio he sent me. Very modest. He did his degrees at Stanford. He did a PhD in Stanford, and then he moved over to Berkeley. That's about it. Then a bit about his research, which you all know pretty well. So I thought a bit how I should introduce you. And I actually know you or your research from my own research in computer graphics. So one of his starting points was in computer graphics. He was publishing one CRV paper a year. So already at the time, it was this person I was looking up to. I was a PhD student starting. My PhD supervisor gave me one of his work as a paper to read. I had to chew on it for quite a bit of time. It was on character animation. And yeah, already using some reinforcement learning. So I guess that's where he went to in the end. And I just now checked the history, and he already had an NeurIPS paper, I think, in 2010. I wasn't aware of that at all. And then a couple of years later, I saw this paper where he connected the camera to a robot and did all this reinforcement learning. Just talking about it on a high level, he's going to tell us much more about it. That was a couple of years later, and I wondered, wait, is that the same Sergey as I was reading the graphics papers of? And yeah, it turns out it was. And he's since then doing amazing work, really inspiring. Particularly this work I was mentioning with connecting computer vision, connecting a camera with the robot and using that as feedback was quite changing the way I was thinking about computer vision. I thought we had to do really good computer vision to be able to do robots, but it seems like you can train these things together, and maybe we just have to get the right robot, the right reinforcement learning to do computer vision. So I'm looking really forward to how this talk will inspire me again. Thanks to you, Sergey, take the stage. And yeah, afterwards we have time for questions. If you have questions during the talk, post them in the Q&A so we can organize them a little bit. If you don't find the Q&A, put it in chat, that's fine as well. We'll monitor that. And yeah, so let's enjoy the talk. Take the stage, Sergey, thanks.
Thank you for the introduction. Yeah, so since we connected the camera to the robot, we've started worrying about the same things that folks worry about in computer vision, which is of course generalization. And that's going to be the topic of the talk today. So let's start with a little thought exercise. Let's imagine that it's let's say 2030 or something. You know, you're some point in the future, and you've just purchased your first home robot. It comes in a box. You take it out, you assemble it, and you give it its first task. You can use your imagination of what it looks like, but the task that you're going to give it is to go and clean up your bathroom. So in the morning, you turn it on, ask clean up my bathroom, and you go to work. And you come back in the evening, and what do you find? Well, the robot tried its best, but your bathroom is kind of atypical. Like you have this little sink in the corner that's pretty different. It's really cramped. And maybe the robot messed up a little bit. Maybe at first it tried to clean up the bathroom, but then it spilled a bucket of water everywhere, and then it spent like the rest of the day mopping it up. And by the time you get home, well, it's a little bit better than it was when it started, but it's kind of not really what you would want. But then on the next day, maybe the robot will try again. Maybe it'll learn from its mistakes. It'll improve a little bit, and maybe the second time around it'll clean up the bathroom better. By the third time, it'll get better yet. And by the end of the week, maybe it's doing this at like you know, with its robotic precision and efficiency. Okay, so that's the thought exercise. The question, of course, is what kind of technologies do we need to develop if we want to make something like this possible? Because there's a lot wrapped up in what I just said. There's the notion that it can just, you know, be placed in your bathroom, and right off the bat, it will do something kind of sensible, but maybe not perfect. And also the notion that with a modest amount of experience in this environment, it'll continue to improve. So can we think of a recipe that could allow for something like this? So we're going to need a good starting point, because without prior training, if you just put that robot in your bathroom for the first time, it's not going to do anything even remotely sensible. So we need to get large data sets of past interactions and use them to bootstrap the best skill we can get. But of course, just like in the anecdote before, that may not be good enough. It may be that it will get a kind of a basic level of competence, but not the kind of competence that is needed to really succeed at the task consistently. And then you need to fine tune from some additional interaction. So what I think we need to make this happen is we need algorithms for learning behavioral skills. These are going to be reinforcement learning algorithms. We need to bootstrap those algorithms off of large amounts of prior data. And then we need to be able to fine tune those policies with a modest amount of interaction in the actual environment where the robot is situated. But there are other things we need too that are also very important. For instance, when the robot spilled that bucket of water on the floor, it knew that now it had to take care of this. It couldn't just keep trying to clean your sink. It needed to now, clean up the spill, fix that all up, and then go back to what it was doing. So it needs a large repertoire of behaviors that it can deploy depending on the needs of the situation. And it needs to understand that if it messed something up in the world before it can try something again, it needs to put things back the way they were. And this might seem like a little bit of a technical detail, but it's actually a very fundamental fact of living in the real world. So in a simulation, you can reset it every time, try things as many times as you want. But in the real world, you have a single lifetime and you have to manipulate the environment continually. And this is where I think things like multitask learning will be really important. Okay, so that's kind of an outline of the problems that we're faced when we try to think of a system like this. Let's summarize these problems into key questions that we can study. The first question is, can we design reinforcement learning algorithms that can use broad and diverse data sets? Can we basically stand up this policy from a bunch of prior data that other robots have collected in all sorts of different bathrooms so that as soon as you put it in your bathroom, it does something kind of sensible? Second question, can we leverage the starting point to rapidly adapt? Can we actually figure out what to do in your particular bathroom? Can, after the first couple of days, can the system actually get better? And the third question, and this is a really big one, I think, can we do all of this fully autonomously in real world settings? Can we do it without essentially a magic reset button, without a simulator, without somebody coming in and fixing things up so that the machine can try again? And it's one of those problems that we don't really think about very much until we have to do things in the real world. So I'll start on these questions in order, starting with the first one. What can we get out of large and diverse data sets? And one of the projects I want to talk about here deals with deriving a sort of common sense from prior data. Let me illustrate what I mean by common sense with an example. Let's say that you would like a robot that slices onions in your kitchen. Okay, maybe this is the second task that you'd like your household robot to do. Now, maybe we trained a controller for this onion slicing robot really, really well. We had it slice hundreds of different onions with lots of different knives. So when it's holding a knife, it knows exactly how to slice an onion. But now you put it in your kitchen and it doesn't know what to do because it doesn't have a knife and there is no onion in front of it. Now, a person would never be confused by this. A person would understand, well, if my job is to slice onions, let me check in the drawers, where are the knives, where are the onions, put things on the table and get to work. But a robot would lack this understanding unless it has some other source of knowledge to obtain it. So somehow it needs to figure out that these simple behaviors that act as prerequisites for the job that it needs to perform, they need to be produced or recalled on demand depending on the needs of the situation. In some sense, that is very similar to what we call common sense. So here's how we can think about this in a data-driven way. If you've learned the skill of cutting an onion with a knife, that by itself is not going to tell you, of course, how to open drawers and how to take out knives and how to take out onions. But you might have some prior data of other things that you've also done in a kind of a multitask setting. So maybe you have experience opening drawers for other reasons. Maybe you've opened a drawer before to take out a fork. Maybe you've picked up a knife off the table before. So maybe you've done other things that can be useful for the task at hand. You just haven't put them together in this way. Reinforcement learning actually already gives us a way to stitch these disjoint pieces of knowledge together to acquire something that actually looks a lot like common sense. If we use standard value-based reinforcement learning methods, we should be able to figure out that the state where the robot is holding the knife is a high-value state because the robot knows if it is holding the knife, it is about to succeed at cutting the onion. And it can use this to link its understanding of this current task to prior data that it has collected. It can understand that if it is holding the knife in the prior data, even if that knife was not used to cut an onion, that also has high value because it's a similar state. And that means that other states that precede that state also have high value. So even though it has never experienced the act of opening the drawer, taking out a knife, and then cutting the onion, it knows that holding the knife is good, therefore opening the drawer is good because that can lead to holding the knife. Now, of course, in reality, this prior data would contain lots of other stuff that is not relevant, maybe making a soup, cutting a carrot, baking bread, these are not useful for cutting onions. But crucially, we don't have to tell the machine this. As long as that chain of high value states is present in the prior data, in principle, a reinforcement learning algorithm should be able to put the pieces together. Now, this might seem like a somewhat obvious explanation of dynamic programming, but it's actually a significant departure from how these types of problems have been explored in the past, because typically these kinds of issues would be tackled through the lens of hierarchical learning or planning, whereas what I'm discussing here is just straight up applying a value-based deep reinforcement learning method to the problem. So let's see if that actually works. Let's see if we can get this kind of common sense generalization of different initial conditions purely through dynamic programming, through deep reinforcement learning. So the particular setup we'll have is a little different, no onions. The task will be to pick up a ball from an open drawer. Now, if you just train to pick up a ball from an open drawer, if the drawer is closed or there's something in the way, you of course won't be able to succeed at the task because you didn't train in this situation. So just like in the example before, we're going to provide the robot with prior data. And that prior data illustrates a variety of other things that could be done in that environment: opening drawers, closing drawers, moving objects out of the way, and so on. Not all of that data is relevant, but it just kind of covers a range of different manipulation tasks. So the setup is that we have training data for our new task, picking up the ball, and that's always from an open drawer. And then we have prior data. So the task has sparse 0, 1 rewards, 1 if you succeed, 0 if you fail. You have to learn everything from images, and you only see the task from a single starting condition. The prior data has no task reward at all, so the reward is 0 for all prior data. It doesn't accomplish the new task, so you never see picking up the ball in any of the prior data episodes, but it does show you how to reach that starting state. So some of the prior episodes do end in the drawer being open. And the algorithm is basically just standard deep RL, with the one exception that we need some algorithmic modifications to make it work in this offline setting, because we don't get to collect more data in those prior settings. We're just given that data in a big bucket. So we use a offline RL algorithm called conservative Q-learning that we've developed for this purpose. But the basic principle is the same kind of dynamic programming principle that underlies all value-based RL. So the results are that the idea basically works. So again, the training task is that you pick up this object from a open drawer. If you start off with the drawer closed, the robot actually understands from having connected its prior experience to this new task that it needs to first open the drawer and then pick up the ball, even though it's never seen those two things together in any single episode. If the drawer is blocked by something, it'll lift the bottle, it'll close the top drawer, then open the bottom drawer, and then lift the ball. If there's an object in the way, it'll first pick up the object, put the object away, then open the drawer, and then pick up the ball. So it can stitch together all these parts and successfully generalize to new initial conditions. So that's something that we can get out of bootstrapping with diverse multitask data. But that was a simulation. Let's try to take some of these ideas to the real world. Can we do learning from large amounts of prior data in more realistic settings? And here I'll also talk about the second question of how we can adapt to particular environments. So the task that we're going to be addressing in this work is to build a robotic delivery driver. So the input to the robot is the camera images that it's seeing and a goal image taken by the user. So you can imagine maybe you want your sidewalk delivery robot to deliver your burritos. You take a photograph of your front door, and then the robot is going to search through your neighborhood until it finds your front door to deliver your burrito for you. So there's no GPS, there's no localization. Everything is being done purely from the robot's onboard images and this goal photograph that you provided it. So the robot has its current observation, it has the goal that you gave it, and it needs to basically figure out what to do in between to reach the goal. So these are some actual examples from our test environments. The leftmost column is what the robot saw initially, the rightmost column is the goal, and you can see it navigating towards that goal. So these are fairly long horizon navigation tasks. And just for your own reference, I'm going to show you these aerial satellite views in many of these clips. The satellite view and the GPS location is not provided to the robot. It's just shown for your own reference, just so you can see what path it's taking. So let's start with that first question again. How do you use broad and diverse data sets? Well, what we can do is we can collect large amounts of data. It actually doesn't matter how. It can be collected autonomously or from demonstration. In this case, we did it autonomously via a semi-randomized policy that just kind of drives around the environment in random directions. And then we're going to use it to train a model that will allow the robot to navigate to these goals. And then I'll discuss how we can adapt this model to a particular environment by building a local topological map, a kind of a mental map of that particular environment. So the prior data will be used to train up a general navigational model. It'll kind of reason about navigational affordances, and then data from the particular environment you're in will be used to build this mental map. So kind of like once the delivery driver has driven around your neighborhood many times, they kind of know where everything is, and that's their local mental map. Okay, so let's talk about this a little more. First, what is the model? Well, the model is going to take as input the current observation and the goal observation, and it's just going to predict two quantities. First, it's going to predict a dynamical distance. This is a quantity measured in terms of time. The units of distance here are time. How many time steps does it think it'll take to get from the current observation to the goal observation? And this can easily be trained on the training data that you're given, because you just take all of your trajectories, pull out every subsequence, measure how many time steps there are between the start and end of that sequence. The start becomes the current state, the end becomes the goal state, and the number of time steps becomes the label. The second output is the action, and this is the action you should take right now. And that's, again, just done by taking the action in the data set. So this is not the most sophisticated control algorithm. It's basically just copying the goal-reaching behaviors in the data. But as long as the data includes very broad coverage, this will actually be a pretty good way to learn how long it takes to get to different destinations and which actions will get you there. But of course, we could substitute any other offline RL algorithm here, including the one from the previous section, and that would probably work a bit better. We didn't find that to be necessary here, but it would probably lead to an improvement. But then we're not just going to use this model directly, because we need to traverse fairly long horizon navigation tasks where we might not even see the goal from where we are now. So we're not going to use this model by itself to reach the goal. What we'll do instead is, in every environment where the robot has to navigate, we'll drive it around a little bit, and we'll build a kind of mental map consisting of the images that it saw, connected by edges, and the weights on the edges are given by these distance predictions. So you can almost think of the nodes here as landmarks. They're just images, and the edges as the traversability between those landmarks. This is not a geometric map. It's not like what you get from SLAM. It's purely a topological map. So crudely, you can think of it as essentially picking out the landmarks in the environment and figure out which landmarks can be reached from which others. Now, all of the training data for this is actually prior offline data. So for this particular project, we didn't actually collect a single minute of additional training data. All the data was actually taken from a previous paper we did for a largely different purpose. But this actually illustrates the benefit of this idea of pre-training your policies on prior data, that you can build up this sort of strategic reserve of all the navigational data you've ever seen and use it to bootstrap this global model that reasons about navigational affordances, and then collect just a little bit of data in your environment to build out the graph. So here are some demos of this approach in action. This is the student Dhruv Shah, who was the lead author on this work, was having some fun with it. He decided to demonstrate a contactless pizza delivery application. So if you, this was in 2020, so we were all worried about the pandemic. I thought, well, if you don't want the pizza delivery driver to, come directly to your door, maybe they can put the pizza on a robot. You just take a picture of your front door and it'll navigate there. Here's a patrolling application. So you take photographs of waypoints in the environment, and then the robot will autonomously navigate between those waypoints. So it's using the mental map to figure out how to get between them. And then when it reaches a particular image, then it goes on to the next one. Okay, but what about exploring new environments? So far I kind of glossed over this problem of how do you get the data to build out that mental map, and that's what we're going to deal with next. So now we're going to be in a scenario where we built out our model using lots of prior training data, but now we're put in a new environment that we've never been in before. So we don't have the mental map. How do we build it? So let's say your current observation is this picture, and your goal is this white door. Okay, well, if you were a person looking at this, what would you say? Oh, I don't know where that front door is. I can't see it in the current observation. I do see a white building in the background, so maybe it's something to do with that white building. Maybe I'll go over there and check it out. So what you're going to do is you're going to search. And the way that we can devise the search method can actually leverage the model trained on all that prior data. So that model trained on prior data will give us some initial expectations about where things might be. Like, for example, the notion that a white door might be on a white building. But of course, it's not enough by itself. We have to actually search the environment, build out our mental map, and then use that. So what we'll do here is we'll actually slightly modify the model. We'll train it so that it takes in the current observation again and the goal. But now the goal will be bottlenecked through a random variable. This is modeled using a variational information bottleneck. And that latent goal variable has a prior. So we can either sample it from the posterior, z given s and g, and then it will act just like the model in the previous section. Or we can sample it from the prior, which intuitively you can think of as selecting a random latent goal that you think is reachable. It doesn't require actually generating an image because it's still a latent variable, but intuitively you can think of it as something in the robot's vicinity that it thinks it can reach. And this is going to basically instantiate that design from before, where all that data from past interactions will be used to train up this model, and then a small amount of data in the current environment will be used to build up the mental map. And the way that small amount of data is collected is by using these latent goal variables. And everything is still trained on the same exact prior offline data set. So we're still benefiting from all that prior data. So first, as a unit test, we can see how well the robot explores if we sample random goals. So as a baseline, we're just going to see what happens when it takes random actions. And here we have a region of Richmond Field Station outside of Berkeley that we used for this. And you can see that it has a radius of a little under 10 meters if it samples random actions. That's a baseline. If it samples random goals from its goal model, the radius is much larger. In fact, it actually covers the entire space. At the top, it's blocked by that pickup truck to keep it from getting out. So let's actually see how this works as a complete method. When we're placed in a new environment, the first run is an exploration run. During this exploration run, it's going to be building up this graph, building up this mental map. It'll sample goals randomly when it's at the fringe of the graph. And when it's not at the fringe, it'll pick rarely visited points on the fringe. So that's why what you see at the bottom is this kind of search pattern where it goes to the edges of the regions where it's been, and from there explores to a random location. Once it catches a glimpse of that white door, then it figures out, there's my goal, so it navigates to it. So it took this very roundabout path because it's searching the environment, but as it does it, it builds up this graph. And that graph now will serve as its mental map in the future. So if it is then asked to reach a goal in this environment again, it can simply recall that mental map, plan it just like before, and on the second run, it can actually reach the goal very quickly. So on the second run, it doesn't bother searching, it actually drives straight to the goal because now it knows where things are in this environment. So that's an example of how this kind of adaptation scheme could work, still enabled by data to help you adapt faster and to explore for the first time, but also benefiting from even modest amounts of experience. Okay. In the next section, I want to focus a little bit on this third question. So far I talked about how we can use large amounts of previous data. I talked about how we can adapt to small amounts of data in a new environment. But in the navigation scenario, we kind of glossed over how to try again, because with navigation, it's fairly straightforward. It's not like you're going to be spilling buckets of water and cleaning them up. But in a lot of more complex manipulation scenarios, this becomes a really big deal. Let me walk you through an example just to illustrate this point. Let's say that you have a robot whose job is to learn how to make a cup of coffee. And perhaps it attempts the task for the first time. Its task is to put the cup in the coffee machine, and it drops the cup. Okay, well, a person could come along and rescue it. A person could come along and pick up the cup and set it back to where it was. But we don't want to require that. We want the robot to do all this autonomously. So maybe what we could do instead is give it a second task. We could say, well, you actually have two tasks. You have put the cup in the coffee machine, and second task is pick up the cup and put it back. So if you fail on the first task, that gives you an opportunity to try the second one. If you succeed on the first task, maybe your next task is replace the cup. And if you fail and you spill the coffee, maybe your next task is to clean up the coffee spill. So by introducing many different tasks that all interact in some way, we can actually enable the robot to practice the whole graph of tasks autonomously, even if every individual task is to come in and reset the environment. This is actually a big deal because in many realistic settings, we want robots to learn large repertoires of tasks. And it's actually quite interesting that moving to the setting where you learn large repertoires actually makes it easier to learn autonomously. So let me illustrate a particular experiment that we did recently on dexterous manipulation that makes use of this principle. So the task is going to be to pick up an object and then reposition it in the palm. Now, of course, if we try to have the robot practice this task, if it has to learn from scratch without any simulation, without any human-provided knowledge, the first thing it's going to do is going to drop the object in some odd corner of the bin, and it won't know what to do about it. So we're going to devise a graph just like before, And this graph is going to consist of 4 tasks: recentering the object in the bin, flipping the object right side up so that it's in the palm, lifting it from the bin, and rotating it in the palm to be in the desired configuration. So once we've constructed this network of 4 tasks, these 4 tasks can now reset each other. For now, the particular choice of tasks and the particular linkages, which task resets which other one, is designed by hand, although in the future we could imagine also learning that through some kind of hierarchical procedure. Once we've done that, we can actually have the entire training process run fully autonomously. So what you see in this video is basically a time lapse of the entire training process for this task. I believe it took about 60 hours. 60 hours is a long time, but it was entirely automatic. So once the robot is switched on, you can go home, get some sleep, do your homework, whatever you want to do. The robot is doing the work, not you. And that actually is kind of an important thing for robotic learning. So far, a lot of robotic learning involves a lot more human manual effort than robot effort, whereas here we're making the robot work a lot harder. We can also do other tasks. So here, same principle. The task is to pick up this pipe connector and connect it to the socket there on the wall. And again, the task is learned entirely autonomously by separating into stages and then linking those stages in a graph and practicing automatically. So the main idea is by learning multiple tasks at the same time, by simultaneously learning this repertoire of behaviors, we can allow robots to learn entirely autonomously in the real world. And once we do that, then real world reinforcement learning can be scaled up with some pretty complicated tasks. Okay, so in the last section of this talk, I want to discuss a little bit some of the experiments that we've done at Google on actually scaling up these robotic learning ideas to much more diverse settings where we could imagine actually applying them to practical real world problems. So the basis for a lot of these experiments is going to be the Qt-opt system that we developed back in 2018. And this is a system for large-scale multi-robot distributed deep RL. So the idea is that we have a data set from all the past experiments that we've conducted in this environment. We have live collection from multiple robots. All the data is pooled together in a set of on-policy and off-policy training buffers. And there's a distributed RL algorithm that is pulling data from these buffers, labeling it with target values for the Bellman backup, and then doing regression. So I'll discuss some of the work on the original Qt-opt system, as well as some recent work that we've done that gets us some of these multitask ideas. So the initial system was designed for robotic grasping, and it was trained on about 1,000 training objects with about 600,000 training grasp attempts. The Q function was represented by a convolutional network with about 1.2 million parameters, which is pretty big by RL standards, but pretty small by computer vision standards. So kind of a good, healthy compromise. But importantly, and this is going to be more important later too, the only grasping specific feature in this whole system is actually the reward function. So the reward function is just 1 if you've picked up an object, and that's the only thing that defines the task. Now, by training the system on a very large set of objects, we were able to get pretty effective generalization. So we could get the resulting policy to pick up a variety of different objects, including really oddly shaped things like this. It's doing this entirely from monocular over-the-shoulder images without any depth sensing. And unlike most robotic grasping systems, it's reactive. So it doesn't just select a grasp point and go there. It actually watches what it's doing, and if it messes something up, it adjusts its grasp and tries again. So that means that it can react to things like nefarious humans pushing the objects around in the bin. The system ends up working really well. It can pick up objects in dense clutter, objects that are large, small, transparent, deformable, etc. And on a pretty challenging test set of never before seen objects, it gets a success rate of 96%, which to my knowledge is one of the best results for a purely monocular RGB grasping system. In fact, those 4% of failures are mostly on the 2 rubber octopuses. So as long as you don't have any cephalopods in your test set, it actually works really, really well. But what we've done recently is we applied some of these lessons that I talked about before and extended this system to multitask settings. So in this recent work, which we call empty-opt, we extended the approach to train on many different tasks. In this case, 12 different tasks centered around different kinds of object manipulation behaviors. So these behaviors all generally involve picking up some particular type of object and relocating it into a desired location. So kind of pick and place tasks with some sort of semantics attached to them. In order to make this work, we're actually sharing data across the tasks. So every episode that the robot collects, of course, it's used for that task, but it may also be shared with other tasks. And the policy has a shared backbone and multiple heads for every possible behavior. So this generalizes QTOP to learn multitask policies with 12 training tasks. We show experimentally that training data improves performance on all the tasks. But then most relevant to this talk, we also study how we can rapidly fine-tune to new tasks. And this turns out to be a lot easier once, of course, you pre-train on many different tasks. So in order to define success for these policies, we use classifiers. So we train a classifier for what it means to succeed in each of the tasks. That's used as the reward function. We have 12 different training tasks. And then once we've set that up, we can run the system with new objects and use that to fine-tune to new behaviors, like putting an object in a bag, putting bottles somewhere, picking up noodles and stuff like that. One of the quantitative results that I want to go into in a little bit more detail is how data sharing in MTOpt improves performance, particularly on those tasks that have the least available data. So this is the performance graph from MTOpt. The green bar is the MTOpt method, and then the blue bar is naive data sharing across all the tasks, and the beige bar is single task learning. Now, all the tasks are learned jointly with offline RL, so this is actually a purely offline RL method. But something to note is that the data is actually ended up being very imbalanced between the different tasks. So some of these lift banana, lift bottle tasks over here, these are the ones over there, have very little data, less than 10,000 episodes compared to some of the others. And these are exactly the tasks where we see the largest improvement from MTOpt. These are the tasks where the green bars are much taller than all the other bars. So intelligently sharing data and performing this multitask learning, as expected, gives us the largest benefit on those tasks that are underrepresented. And it improves performance massively on those tasks. So this is getting at some of the bits that I alluded to before, that if we bootstrap our model from diverse multitask data, then maybe some of the generalization that we'd like to achieve can be easier. Here's an illustration of how some of this data sharing happens. So if you picked up this soup can and dropped it in the plate, that's a success for picking up anything. It's a success for placing anything. It's a success for placing anything in that particular corner of the plate. And then it's a success for whatever other tasks are relevant. And then you can pick a new tasks like draping this cube with a towel and run some existing tasks on to see if they succeed, use that to collect data, and then fine-tune a policy. So the total range of things you can do with this system is actually very large. This is kind of a montage of different behaviors that we get out of this thing. But maybe that's not enough. Maybe we want to push things further. Can we further automate even the task specification stage? Can we get rid of this need to manually specify that there's 12 tasks and we have classifiers to define the rewards for each one? What if we go back to a recipe similar to what we had in the navigation scenario, where we train a policy conditioned on a task goal? So here we're going to have no reward function at all. The task is defined entirely using goal images. So just like before in the navigation case, a user shows a picture of what they would like to see happen, and then the robot takes the steps to accomplish that. Here the goal image is shown in the column on the left, and then the film strips on the right show the execution. This is going to use the same conservative offline RL method, essentially, with some modifications, but basically the same principle as we used before for that common sense project. This is based on conservative Q learning. The reward is not provided by the user, it's just relabeled from the data set. And it's going to actually use exactly the same data as the MTOpt project. So just like before, one of the big benefits of employing offline reinforcement learning algorithms for these tasks is that we don't need to collect new data. We can just take the data we had before, modify our algorithm, apply it to that, and get results. So here's a video of what happens with the system, which we call actionable models. So just to set this up, on the right-hand side at the top, so top right is what the robot is seeing. Bottom right is the goal image specified by the user. Sometimes looking at these, you have to kind of take a little time to see what's going on. So currently the robot is not holding anything in the gripper. The goal image in the bottom right has the robot actually holding the bottle. So this goal image tells the robot pick up the green bottle. And indeed, that's what the robot does. In fact, it actually regrasps the bottle a few times to pick it up by the right part, because initially it picks it up by the neck. Here it's asked to pick up the carrot. Here it's asked to pick up the corn cob. Here it is asked to pick up the broccoli. Lots of food objects. Here it's tasked to pick up the carrot and place it in the plate. So it takes a little while to get it right, and actually positions the gripper so that it drops the carrot in the correct horizontal orientation. Here it has to drop the banana. The banana is actually backwards, but it's still roughly aligned along the same axis. Here it has to drop in the broccoli. Here it has to move the banana next to the carrot. And you can see it's a little bit kind of obsessive about it. It actually tries to reposition it to get into just the right spot, which is pretty neat. Same idea. It actually works pretty hard at repositioning the carrot here in just the right place so that it matches the goal image. And it's not content until it gets it just right. Now, of course, you might say at this point that specifying tasks with goal images is a little bit annoying, like who's going to do the task, take a picture just so they can tell the robot to do it. A big part of the benefit of this kind of approach is that it can serve essentially as unsupervised pre-training for RL. So we know that in domains like NLP and computer vision, unsupervised pre-training is a really powerful tool to use data without human labels to initialize a model. That's what we're going to do here. We're going to use this goal conditioned learning, which doesn't require any human provided rewards, as essentially unsupervised training. So we'll train our goal conditioned Q function, and then we'll basically fine tune it on a task with a human specified reward, but where data is more limited. The actual implementation we use, actually, it doesn't do pre-training and fine-tuning, it actually does joint training. So it just uses both losses at the same time, but we can do pre-training and fine-tuning also. So there's two heads, a goal condition head and a task-specific head. The blue one, the blue curve shows what happens with the task head and the goal head, and the orange one is just the task head. And you can see that the method is much more efficient and reaches better performance when it utilizes this unsupervised goal condition stage. All right, so where do we go from here? I talked about these three questions. Reinforcement learning algorithms that can use broad and diverse data sets. How can we get them? How can we bootstrap the model so that it does something sensible right out of the box? How can we leverage the starting point to rapidly adapt to new tasks? And how can we do this all autonomously without having people come in and fix things up for us? So I discussed how using prior data can get us this notion of common sense. I discussed how we can use large amounts of prior data to learn these general navigational affordances and then fine-tune them to a particular environment by building this non-parametric mental map. How we can do all this autonomously by building a graph of tasks that all reset one another, and how we can scale this up with large-scale, parallelized, and multi-robot deep reinforcement learning systems. Now, there are many parts to this recipe that I haven't talked about, and there are also many parts that we haven't figured out yet. So there's a lot more left to do. One big component, of course, which I didn't talk about in detail in today's talk, is the algorithmic foundations, right? So most of these things that I showed use algorithms for offline reinforcement learning. There's been a lot of work on that topic lately, but a lot more research is needed. So these algorithms do still have pretty major limitations. When we think about fine-tuning from additional interaction, the approaches I showed, they were fairly simple. We needed to keep them simple to scale them up to big robotic systems, but there are much more sophisticated directions to explore there, like meta learning, like learning to explore and things like that. We need to think about where we get these data sets. So far, we're still collecting them kind of bespoke for every experiment, although we're seeing more and more reuse. But we could also think about how we as a community can standardize data sets for robotic learning. We've taken some steps in this direction with a project called RoboNet. There are other projects out of places like Stanford that collect large data sets of demonstrations. And maybe we as a community should think about how to pool those, how to collate them and categorize them appropriately. My concluding remark here would be that with these three questions, I think addressing these challenges really does have the potential to bring us closer to truly in the wild robotic systems that can generalize broadly, they can perform diverse tasks, and they can do all this autonomously with minimal human improvement. And when they can do this autonomously, they can just keep getting better and better. And once we achieve that, that'll be tremendously powerful. Thank you very much, and I'd be happy to take questions. So we're truly in the wild robotic systems that can generalize broadly, they can perform diverse tasks, and they can do all this autonomously with minimal human improvement. And when they can do this autonomously, they can just keep getting better and better. And once we achieve that, that'll be tremendously powerful. Thank you very much, and I'd be happy to take questions.
Thanks a lot, Sergey. Amazing talk. It's fun to watch these robots. They look so natural, and then that's also scientifically so deep. Yeah, so if you have any question for Sergey, put it in the Q&A. If you like a question particularly, then vote it up so it comes to our attention. We do have time to discuss a bit. Let me take the ones we have so far. Maybe I go back to forth in time. So this was a question when you were talking about the third project you presented, and that attendee wondered whether the 1.2 million parameters that you mentioned, whether they are somehow predefined or at least initialized somehow. I believe it would also be interesting to see.
Yeah, that's a good question. So in that particular project, the whole queue function was trained entirely with RL. So there's no initialization, there's no kind of prior thing that's fed into it. We did find in some previous projects that, using, just like in computer vision, using pre-trained features from something like ImageNet does help. In that particular project, it actually didn't, because the grasping data set is larger than ImageNet. Significantly larger, about a factor of 10 larger. So we can actually just train it on that data, and it's fine.
Yeah, that's an interesting answer. Also related to what you said at the end, that the robots will autonomously learn. So I wonder what you think about computer graphics. Currently, RL is relying a lot on graphics. Will we need that still in 5 or 10 years, or is it also obsolete and we can really learn on real data sets?
So you're asking about utilizing simulation for bootstrapping these behaviors. Yeah, that's a really good question. I think that, my answer to this would be something like this. I think that where we are today, like if you're sitting thinking about how do I get an industrial robot to do bin picking, or how do I get an industrial robot to do car assembly, using simulation is a very pragmatic way to go. And I think it can get you really far today. I think longer term, algorithms that utilize data in place of simulation will catch up. And once they catch up, there's actually a lot of good things to be said about relying mostly on data. And that's what we get, that's what we have today in fields like computer vision and natural language processing, right? We don't worry about simulating computer vision data as much. There's some research on that, but that's not kind of the primary go-to approach, just because the real data is so useful. So I do think that there is a place for simulated data. In some domains, there will always be a place for it. So if you want to use RL to train like the Mars rover or something, you're not going to send the Mars rover to Mars 100 times. But in a lot of other domains where we can leverage data, I think it'll be a really powerful tool, and it will greatly diminish the need for some of the simulation.
Liam turned on the video. I think you had a question as well.
I have like several questions, but let's see where to start, I guess. Really amazing work, Sergey. Always love seeing your talks. I might have asked you this before, I actually forget, but like one of the key, cornerstones of probabilistic robotics is like reasoning about uncertainty. And when I see this paradigm that you present, I don't see any explicit reasoning about uncertainty. So what's your view of this, of the role of uncertainty within this more learning-based, data-driven paradigm?
Yeah, that's a good question. I have an easy answer and a complicated answer. So the easy answer is that, well, a lot of the, if we open up, I guess when I was in graduate school, the book that I would open up is probabilistic robotics, right? We all know and love it. There's Bayes filters, there's particle filters, all the bread and butter of modern robotics. Most of that is concerned with state estimation. Now, is the convnet that we have, for example, in the navigation setting, is it doing something like Bayes filtering under the hood? Well, I don't know, but you could say that insofar as you need Bayes filtering to be successful at localization, if it's successful at localization, it must be doing something like that. So to some degree, the easy answer is that large high-capacity models, if they need to implicitly represent uncertainty, they can do that. They have the representational power for it. But I think there's a more complex answer to this, which is that besides state estimation, which is a very particular specific problem in robotics, there's the broader problem of dealing with uncertainty when it comes to generalization, robustness, safety, things like that. And I think those are actually the really big things where uncertainty really matters. So, giant convnets, it's a simple recipe. Like, you give them a job and they do that job, and they will do whatever is necessary to solve that job. But when it comes to seeing things you've never seen before, now the problem is it's hard to even define what that job is. So there, when you need to reason about epistemic uncertainty, that becomes much more difficult. And there is actually a lot of research in the deep learning community with things like Bayesian neural nets that deal with those kinds of things. We're working on some things right now, actually, for NeurIPS that study the importance of epistemic uncertainty for generalization in RL, and there's some really deep questions there. So I don't think that reasoning about uncertainty is going to go away. I think it'll just shift from dealing with state estimation to dealing with unpredictability, robustness, all those nasty things that happen at tests.
We are losing the connection a bit. Maybe in the meantime, I can take. It seems to be back.
I think what you said makes sense. Do we still there? Do you hear us?
Yeah,
okay?
I think. Okay. All right. We have another question in the chat from Sefer, and he's talking about this banana repositioning example where the robot grabs the banana and observes that it focused so much on positioning the banana correctly, but we as a human wouldn't do that. So.
Yeah. So this is sort of the dark side of employing a largely unsupervised method, is that it can only derive signal from things that are readily grounded in the pixels. So literally speaking, what the robot is trying to do is like make the image match the goal. So it's going to like fine tune how it's grasping the banana. Yeah. Now, that by itself is a weird way to specify a task. The main reason we did it that way is because it's very scalable. I think in reality, if you wanted to use something like this, you would either do this kind of two heads joint training or fine tuning setup, or you would use the goal conditioning as a cheap and plentiful source of training, and then add some other expensive source that is more like what you want, like, for example, natural language or something like that. And we've actually been experimenting with natural language conditioning for this, and it basically works. It does more or less what you expect, but of course it requires manual annotation.
Oh, well, yeah. So this dual head you mentioned, that helps to get around this very
well, yeah.
signal.
So the two heads thing is what it's basically doing is it's learning some task defined by a reward function, but it's assisted by this goal reaching thing, which is shoves the right representations of the model, making the learning of the main task much easier.
We had one early question that was all the way when you were talked about building this mental map, and I think you answered it somehow, but perhaps you can comment again from Chris. Does the map have to be complete, or can it reach a place where no waypoint is visible?
Well, the trade-off there is basically what you would expect. So if you have some part of the environment where you don't have any nodes, then you won't know what's there. So roughly speaking, as a crude heuristic, you can kind of think of this model as doing like line of sight. Like if I can see the goal, I can drive to it. So as long as all the major parts of the environment are connected by these line of sight lines, then you're okay. It'll still do intelligent local things like drive around obstacles, but if it doesn't see where it's supposed to go, it needs to rely on the graph for that. So I suspect that if we wanted to go deeper on this, we could borrow lots of lessons from things like probabilistic roadmaps and robotics and really get this right. But I do want to emphasize that the map really is a topological map. So it can be, it can have a lot of gaps, and it can be fairly abstract. So as long as you can see the things.
I actually had a follow-up, if that's okay, because we're working on something quite similar. And what we're finding is
that for NeurIPS.
It's not for NeurIPS, no, but Coral or whatever. I guess there's some kind of traversability model that you have in there. And what we're finding is that it's pretty hard not to get false positives out of your traversability model. And I guess I noticed in the experiments that you showed that although there was different traversabilities of the areas of the environment, it was largely wide open space where most spaces were traversable, unless maybe I misinterpreted. But did you have this problem of having false edges in your topological representation? And if you did, how did you deal with it?
Yeah. Good question. So that problem definitely happens. And partly it is because of uncertainty. It's because the standard techniques like search on the replay buffer for doing this kind of stuff, they don't actually incorporate uncertainty properly. And I think they should, and there's probably some really nice extension that could enable that in the future. We didn't deal with that in a principled way in that particular work. We actually did something very simple. We just heavily pruned the graph. So in a lot of the prior papers in reinforcement learning that build this kind of graph using a Q function, they build a pretty dense graph. We built a pretty sparse one because the local controller is actually decent at kind of medium range navigation. So we just pruned it enough and it was okay. But I also do think that there could be environments where this thing could be pretty bad, where you really, kind of like a maze environment where you see the path to the goal, but you actually have to go all the way around. And that would probably mess this up. Like we need a little more to handle that.
Yeah,
Okay.
we're trying to apply this in indoor environments where it's quite a lot more constrained. And so I guess we run up against that.
Mm-hmm.
I have another one. I guess we take turns, unless we do give the audience time if you want. Otherwise, we take it. So I had a question. You do a lot of offline reinforcement learning, and obviously that's working very well. But I have a conceptual question, and I wonder whether this is this rather a shortcut, because that way, if you work with offline data, you get results much quicker. I've seen that in computer vision. Sometimes the simple models, they aren't as good in itself, but then we can iterate so quickly, so we find something new, and it gets much better than this huge bulky system, which is good at this one task, but then really hard to adapt. So I wonder, is this offline learning a quick thing to get to publish, and we want to do something else in practice, or is it really the thing what we want to do?
Yeah, that's a really good question. I think there is like a very pragmatic element to it, and there's kind of a deeper element. The pragmatic element is kind of what you said, that it's like, robotic learning, in my opinion, real world robotic learning, it's partly an enormous pain to work with, because we have, each time we do a project, we have to like collect new data, we have to, stand everything up from scratch. And that's extremely time consuming. That really slows down progress. Whereas in computer vision, we just grab an existing data set, try out our method, and get results. So that allows the community to progress a lot faster. So I do think that offline RL has a huge benefit in that regard. But I think there's also a deeper element to it, which is that once we can do that, once we can iterate that way, we will be tempted to work on different problems where we have large data sets and generalization, which computer vision kind of takes for granted, but in robotics is actually a fairly rare thing. So the pragmatic thing right now is that, yeah, we can make faster progress, and that's great. But the deeper thing longer term is that we'll actually work on different problems, ones that are more relevant to the real world. And that, I think, is actually really important.
So we shouldn't be too focused on that direction, but always keep in mind that there's a world beyond this data set.
Yeah, I think so, yeah.
Okay.
I don't know. Let us know if you have to go. But so kind of connected to that, I was thinking when you were talking about the conservative Q-learning work, the prior data that you have, it's still in the form of robotic episodes of doing something. Maybe it's not the exact task that you're trying to solve, but if I understood correctly, the data set is still the robot doing things. And I wonder what you view as the possibility of combining different modalities, or even just purely observational data to build these kind of general purpose representations that can then be leveraged by the robot to take action, at test time.
Yeah, that's a great question. I think that's actually a really promising direction for this stuff. My former student, Chelsea Finn, she's at Stanford now, she's been doing a lot of work on this topic actually recently, using things like video data sets from computer vision to augment training for robots and to demonstrate that there's benefit that can be attained that way. I think it's actually really promising. And perhaps ultimately what we would have is we would take all the data we have from robots, all the data we have from other sources, and kind of use that to distill the best possible understanding of the world that the system can get to serve as a starting point for whatever it needs to do.
Yeah, that makes sense to me.
Yeah, I think this is a good ending point. Still seeing some promise for the vision data sets, at least, to incorporate that. So yeah, thanks again, Sergey, for taking the time. Amazing talk. We will put it online so that everyone can listen as well.